Here we're going to start looking at earthquakes. We're going to start kind of comparing them to the frequency and I want you to notice that this is the IRIS seismic monitor map. And these are very common. These are earthquakes that are taking place in the Pacific Ring of Fire. But they're taking place along these plate boundaries. And I want to take a look here and identify that when earthquakes occur, they just happen where we have these plate boundaries of geologic activity. So we'll apply this to tsunamis and we'll find that the Pacific Ocean is very, very ripe for tsunamic activity. But here goes. When we calculate the magnitude of an earthquake, we're really looking at the magnitude that references how much energy was released in the earthquake. And this can be found using two pieces of information. If we know the distance to the epicenter, and we know the amplitude of the arriving waves at a seismogram, we can essentially connect the dots and find where it crosses through and determine the magnitude. Now, the magnitude here is generally associated with the Richter scale. That the further one is from the epicenter, the less shaking or the less energy there is in the seismic waves. Therefore, it would have a smaller magnitude at a greater distance. And you'll see that as this goes down, you would find that its magnitude would go down, and so on. If you decrease this side, the numbers go down as well where it crosses through. But it's kind of interesting how technology and remote sensing technology, we no longer have to be at a location on Earth to determine what's going on there. That we can follow the wave on Earth's surface done remotely. So technology allows scientists to follow waves traveling on the Earth, primary waves, secondary, Rayleigh, and Love, or your surface waves, as they move within rock and get recorded at seismic stations. And when we apply this to a tsunami, when a tsunami is generated, ocean waves can also be followed on ocean surface, coupled with an early warning detection technology. We can study and use information from buoys in the water and seismic equipment that identified that an earthquake took place. So when we compare magnitude versus intensity, magnitude, we're looking at Richter scale and moment magnitude. That the Richter scale is a logarithmic scale that determines the energy of the earthquake. However, it kind of breaks down for large earthquakes. And the moment magnitude is a scale that determines several features of the earthquake. It's a more updated and modern way to view the earthquake. And these are used, moment magnitude are used for large earthquakes. If we compare them to a modified Mercalli index, the Mercalli index determines the intensity of destruction from the destruction point of view along with how people felt the waves. It's fairly subjective due to the building design, right? Some buildings are more easily broken apart than more technologically engineered. The distance from the epicenter and what the structure was built on, solid rock versus soil and or gravel. So the Richter scale. The Richter scale is a scale that used to find out how powerful an earthquake was. That's determined by seismographic readings, and it provides an amount of energy released at the source of the focus. So here's what we can look at. It measures the energy of the waves emitted by the earthquake. And so the small earthquakes from 0 to about 2 can only be detected by a seismograph. And where from a 2 to 2.9 you might just get some mild swinging. Where a 3 to 3.9 would be compared to like a passing truck. And a 4 to 4.9 may break windows, may cause small objects to become unstable. And 5 to 5.9, furniture moves, things may fall from the wall. 6 to 6.9, there may be damage to structures. 7 to 7.9, buildings get displaced from foundations. 8 to 8.9, bridges get destroyed. Strong structures get broken completely. And 9 and over is total destruction. The Richter scale, named by Charles Richter, his life was 1900 to 1985. It's one of the several very closely related methods that seismologists use to qualify the magnitude of the earthquake. That the Richter scale is generally measured from a 1 to 10. That 10 would be extremely powerful. That an earthquake with a 10 would lead to total devastation. But technically there's no upper or lower limit to the Richter scale. So the Richter scale itself, if I look at this here, we consider them a little differently. That the 8 and above are considered extremely great. These are tremendously powerful. Whereas a 7 to 8 is considered major, 6 to 7 are strong, and you can read these moderate to small to minor to not felt at all. So the Richter scale is a logarithmically based, which means that it's a tenfold increase in amplitude of the wave. That corresponds to an increase of 1 on the magnitude scale, which equates to a 32-fold increase in energy. So for example, a 6.5 magnitude earthquake has 10 times greater amplitude than a magnitude 5.5 and releases or generates 32 times more energy than a 5.5. But if I were to compare yet an even 7.5 to a 5.5, we would say it has 100 times greater amplitude of the shaking and yet 1,000 times more energy released in the 7.5 than a 5.5. The moment magnitude scale. The moment magnitude scale is a more precise measurement of how energy was released at the earthquake focus. It's based on 3 conditions. the average amount of displacement along the fault, the rupture surface, or the area, and this is generally measured in miles, and the shear strength of the faulted rock, a measure of how much energy a rock can store before it slips and releases the energy in the form of an earthquake. So really number 3 is kind of like saying we can insert Richter in here. The energy, the rupture surface area, and the displacement location along the fault. And the moment magnitude earthquakes are much better for describing large earthquakes. And when these occur, in this case, like a thrust fault, we can generate a tsunami. And we'll look at what a tsunami is here in just a moment. But as soon as you displace rock at a particular location that we call subduction zones, we can have these tsunamis generated fairly regularly. That's not uncommon. And these take place at these locations here where we have subduction taking place, but this plate here that's being subducted upon is going to buckle. And we'll talk about that here in a moment. So a moment magnitude. When we compare the Richter to a moment magnitude scale, we can find that they generally don't agree with one another. That in the New Madrid, which is a local seismic region to us in Illinois, Richter scale might be 8.7, but its moment magnitude is 8.1. And you can see that these don't necessarily agree, whether larger or smaller. Richter scale here in Alaska, 8.4 Richter, 9.2 moment magnitude. But we're really comparing how much, comparing it to the energy release of an explosive, we're looking at going from very, very mild energies to very, very large energies. So we're really looking at the magnitudes increase very, very quickly. And lastly, the modified Mercalli index. This scale was developed using California buildings as its standard or its proxy. It is appropriate for use throughout most of the world to establish the strength of an earthquake. So the intensity scales are based on the effects of destruction of the earthquakes that depend on the severity of the ground shaking as well as population density, building design, and the nature of the surface. In other words, what it's built upon. That these can be relatively subjective. That sometimes you might feel the same earthquake might do very little, might not be felt and do very little damage in one place, but yet can be completely devastating very nearby. So there's a relative explanation for them as well. So what happens when an earthquake takes place underwater? Well, generally, we talk about it creating tsunamis, these walls of water. So what causes a tsunami? Well, a tsunami is a large wave that is caused from the sudden motion transferring energy to water quickly and efficiently. The sudden motion is most commonly an earthquake, and generally we call this a thrust fault. But a tsunami can be generated by powerful volcanic eruptions, underwater landslides, and even impact events such as a meteorite hitting the ocean. It should be no stranger to you to realize that the Earth is covered by water here. So if an asteroid, a comet, or an impact or a meteorite were to hit the Earth, it could generate a tsunami just simply as a function of the Earth is covered primarily by water. And that energy then is transferred into energy that we call waves. Tsunamis travel across the open ocean at speeds greater than airliners or jets. Upon reaching a coastline, the topography can lead to waves building up and generating wave trains that spill onto land, doing tremendous damage to life, properties, and structures. And here we can look at this in kind of slow motion. That we have subduction taking place. The continental crust is going to buckle to some degree, and eventually it's going to kind of snap back into place as it rebounds elastically. And this is consistent with the elastic rebound theory, that this rock doesn't want to change its shape. It'll bend a little bit, but when it snaps back, that energy is then transmitted into the wave of water. So when we look here, on this map here, we can look at 3 locations where we find thrust faulting. And these are locations that have had or generated tsunamis in the last several, so let's just say 50 years. And these are called thrust faults of land generating the tsunamis. In the picture, an earthquake in Chile generated a tsunami that traveled through the Pacific Ocean and led to a wide range of tsunamis along many coasts. So when we see this area here, it buckles, it snaps back, it releases this wave, and the wave travels. If you can see these areas here, the wave travels through the open ocean as fast as a jetliner. So if we look at a cross-section of the coast during a tsunami, we'd see that there are very large wavelengths as they're coming in. And that often leads to water drawing off, exposing more beach. But when the wave eventually catches up, it comes into contact with the ocean floor. And this is where the topography change increases the amplitude of the wave, or increases the wave height. So a tsunami can travel over 600 miles per hour in the open ocean. This is as fast as a jet flies. It can only take a few hours to travel across an open ocean. A regular wave is generated by imbalance of heat, creating wind. These only travel about 60 miles per hour. But once the tsunami reaches the shallow water near a coast, it slows down. and the water at the top of the wave moves faster than the bottom, causing the wave to rise dramatically. And that's what we're seeing in this picture here. So it pulls water back, then the incoming wave comes, it builds vertically, and we get these tremendous amounts of water that run through here. And this is what we call run-up. The run-up is the water that sloshes onto land. Notice land is higher than sea level. It eventually sloshes back, bringing everything with it. So in 2004, the tsunami in Sumatra, we can actually watch or observe waves that travel all kinds of crazy location. Just by observing the wave pattern here, we can see it traveling through the open ocean. And it's traveling, like I said, that of a jet airliner. And there's tsunamis that are occurring all along these shorelines as it encounters a shallowing topography. We can observe this one here. Notice that over 200,000 lives were lost in the 2004 tsunami generated near the island of Sumatra in the Indian Ocean, and it traveled outward extremely fast. Notice we even have a reflection taking place here. These are all circular waves. Notice when it comes in contact with object, it literally just is devastating walls of water. And you can watch that on your own. In 2010, there was the Chilean Tsunami. This is an area here. This is a slip pattern for the 2010 Chilean earthquake. The black rectangle here encloses an area of the Earth's surface directly above the section of the interplate thrust fault that ruptured on February 27, 2010. The red lines offshore are the fault surface trace right in here. And the line which the fault slipped as much as 14 meters or 46 feet. And the red star indicates the epicenter. The red star right here, which here's a larger map if we zoom out. And the gray dots were the aftershocks and their relative magnitudes. And here's the animation we're showing. If you take a look in here, these are just these waves, these walls of water that are moving through here. And you can watch that video as well. So waves build upwards, and I just want to make sure we emphasize this, that an incoming wave is traveling extremely fast with a very large wavelength. And when it comes into contact with the ocean bottom, it slows down. And the water on top only has one place to go, and that's up. So that it travels really fast in deep water, but the tsunami's energy flux is dependent on its wave speed and its height, and this remains constant. So therefore, if the speed's changing, the wave height must change proportionally. So as the speed diminishes in shallower water, its height grows. And this is called a shoaling effect. A tsunami, imperceptible at sea, may grow to be several meters or many, many feet near a coast. And when it reaches the coast, it appears to be rapidly rising in height due to the frictional drag of the floor. The fast-moving water behind it continues pushing forward. And on this last slide, you can take a look at the dynamics of what's taking place here. This is a really good 5-part video that you can watch on your own. You can just double-click on these and watch the YouTubes. So there you have it on earthquakes, magnitude, intensity, and tsunamis.